The two orbit around each other like whirling dervishes. These binary black holes will eventually collide and coalesce.
It's believed that collisions between black holes will be quite common. They would be in orbit around each other and then spiral inwards, and at some point they would coalesce. And that coalescence creates a huge disturbance in space-time.
If you have two objects that are bending space a lot around them, and they merge together, then you'll get this ripple, this wave going out, carrying energy with it.
Typically, when black holes collide, they create wild vibrations called gravitational waves, which spread across the fabric of space and time.
These ripples would be just like the ripples you would have, say, on the surface of a pond. If you threw a pebble into a pond, it creates a disturbance, and then you see the ripples carrying that disturbance away to far points of the pond.
In the past, binary black hole collisions were impossible to identify. Now, scientists have developed gravitational wave detectors to track these vibrations and hopefully catch black hole collisions in the act. LIGO is a ground-based observatory that's currently searching for gravity waves produced from collisions involving stellar-sized black holes, a few times the mass of our Sun. The system uses lasers to measure the motions of mirrors that hang by wires from overhead supports.
When two black holes merge together, they'll release these gravitational waves, these ripples in the shape of space. And as the ripples pass by these giant contraptions, they alter ever so slightly the distances between these detectors, and the detectors can actually monitor and see that change in distance. And that's the signature of a gravitational wave coming by.
In the future, LISA, a joint NASA and European Space Agency mission, will be able to detect waves from collisions involving supermassive black holes. These impacts occur after two galaxies have merged, and their supermassive black holes sink to the center of the newly formed galaxy and find each other. And if collisions involving two supermassive black holes isn't chaotic enough, try three. In January 2007, US and European satellites actually observed black hole triplets, 10 billion light years away in the Virgo constellation. They're actually three quasars, which are luminous objects thought to be powered by supermassive black holes located in the centers of galaxies. This trio is in close proximity to one another. They're only about 100,000 to 150,000 light years apart, which is about the width of our Milky Way. In all probability, the three will eventually engage in a hostile merger.
If you take three large black holes, brought close together because two big spiral or elliptical galaxies have slammed together, then it's a real free-for-all. And two of them could win the game and throw the third one out.
Gravitational interactions between three bodies can lead to the ejection of one of the supermassive black holes from the system. And then you're just left with a binary supermassive pair that will coalesce ultimately. The supermassive black hole that gets ejected is ejected typically with enough speed that it can't carry stars with it. So it becomes a rogue black hole. It's off on its own.
Modern science continues to unravel the mysteries surrounding black holes. But for some, one enduring question remains.
The deepest question in all of black hole physics is what lies on the other side of a black hole? What happens if you throw the encyclopedia into a black hole? Is all that information lost? We don't know for sure.
According to Einstein's general relativity laws, nothing can ever come out of a black hole. But if a black hole is extremely tiny, the laws of quantum mechanics merge with the laws of general relativity. Quantum mechanics governs the world of the very small, such as electrons, neutrons, and other subatomic particles. General relativity rules the world of the very large, where ordinary gravity is dominant, like planets, stars, and galaxies.
The fact is, when you put together quantum theory with black holes, you find that they aren't completely inert objects that only suck things in and nothing comes out. They actually radiate.
The black holes that radiate are called mini black holes, which are much smaller than their stellar mass or supermassive black hole cousins. Celebrated physicist Stephen Hawking proposed that if mini black holes exist, they must emit radiation, which has been named Hawking radiation. It is believed this radiation will cause a tiny black hole to evaporate and potentially disappear. Hawking gave mathematical evidence that when a tiny black hole forms and then evaporates, some of the information that went into the black hole never comes back out. This startling prediction caused a firestorm among physicists because the laws of quantum theory insist that information can never be completely destroyed.
Essentially, the world split into two camps. Those who believed that Hawking's calculation was really it, and the other camp that said, well, Hawking's calculation needs refining. String theory and other theories seem to suggest that the information is actually preserved. It just comes out very subtly.
The question of what happens to the information that goes inside a black hole is, I think, not fully settled. The chemical composition of the objects that went into the black hole and other aspects of them, their color, their temperature, etc., etc. We don't really know what happens to that information.
It appears unlikely that scientists could venture inside any black hole and return back home in one piece to report their findings. But a worldwide collaboration of scientists may be on the verge of the next best thing: manufacturing tiny black holes right here on Earth. Today, scientists are pushing back the boundaries of cosmic research. If naturally formed black holes aren't scary enough, what about a black hole factory? In Switzerland, at the physics laboratory called CERN, scientists have built the Large Hadron Collider, the biggest, most complex science experiment ever constructed. It's a particle accelerator, 17 miles long and the weight of 5 jumbo jets. It's capable of crushing subatomic particles together to replicate the energies that existed microseconds after the Big Bang. This particle collider was designed and built to study important questions in fundamental particle physics. But it will cram so much energy together that if physicists are lucky about how nature works at those energies, it could also produce tiny black holes.
We might be able to see microscopic black holes being formed in these high-energy collisions, and those black holes would then be amenable to study. They would rapidly evaporate. We'd be able to study their decay products and understand physics of quantum gravity in the laboratory, which is something that we never dreamed we'd be able to do in our lifetimes.
But the possibility of manufacturing mini black holes